Assalamu alaikum ji, this is Muhammad Numan Aslam Khan, and this is lecture 12 of our course, which is Numerical Methods. So we just have a recap of the previous lectures we have done. So we are started with the topic number 2 of this course, which is solution of the system of equations. And in the system of equation, we started with the linear case because we got two cases, namely a linear system and a non-linear system. And in the linear system, we started with one of the technique that you already done in your previous course, which is the Gauss elimination. Okay, but we have seen that there are problems with the Gauss elimination when the pivot element is 0 or it is a smaller number in magnitude. Okay, so we have problems with that. What are the problems? The problems are that when you try to divide by number 0, for example, if the pivot element is 0, you got an infinity, so you will not able to solve a problem. And if, for example, that number is near to 0, for example, it is in 10 raised power minus 10, let's say. So if you divide by 10 raised power minus 10, when it comes to the numerator, it will be 10 raised power 10. So the number will higher in magnitude. Okay. So whenever the number is higher in magnitude, uh, then when you try to round it off up to certain decimal places, then you got a lot of round off error. Okay, and that round off error will leads to in the complete process will leads to a very huge error. Okay, that we have seen in the last lecture, that a solution that we got is very much deviated from the actual solution that we analyzed. Okay, so this happens when we try to not make the pivot element uh, a, a bigger in magnitude in that particular column. Okay, so we devise a strategy which is we call the partial pivoting, which says that whenever you see any pivot element, see the in that particular column, see the elements below the pivot element. In if they are higher in magnitude, bigger in magnitude, just swap the rows. Okay, you can swap the two rows. Okay, so that we have seen in the last lecture. And let me just give you quickly an example of what happens when we got bigger numbers in magnitude. So for example, we have a number 4299. Okay, let's just try to consider that you have a machine which can only display up to two decimal places. Okay, so if it can display up to two decimal places, so it means the number it will show to this original number as 4.2 into 10 raised power 3, which is this number. So if you just see how much error we got an error of 99. Okay, so that's happened when you try to round off the bigger numbers. Okay, and due to the limitation of your machines, you end up being having a lot of error in the process. Okay, so that's why we wanted our pivot element to be a smaller number, a greater number. Okay, not a smaller number. Okay, because ultimately that number smaller in the denominator will be a bigger in the numerator. When you divide by it, it will be a bigger number. Okay, so that is actually a problem that we encountered by having a smaller pivot elements in magnitude. So we devise a strategy which is called the partial pivoting. Okay, I'll just have an example of how we can solve, for example, apply a Gauss elimination. You know how to apply a Gauss elimination, but with an extra condition that you have to impose the partial pivoting. Okay, so in this particular lecture, we will try to reinforce the significance of the partial pivoting in solution of the linear system of linear equations. Okay, which first is the Gauss elimination. Okay, and then we'll try to implement this strategy into LU factorization. Okay, which is another way of solving the linear systems. Okay, so coming towards, for example, we have a system of equation, and we got three unknowns, three equations, and we convert into an augmented form. So this is the first step of the Gauss elimination. And if we just see that, so this is, if you just try to divide it, this is the right hand side, okay? So if you just see a number over here, it is 0. So what is the first pivot element? This is the first pivot element, which is 0, okay? So we can't have pivot element as 0. So we have to swap the rows. But the partial pivoting says swap the rows where in you got a number higher in magnitude. So you see a minus 5 is a bigger number in magnitude, it's 5, okay, as compared to 3, okay. So what we're going to do is we're going to swap rows 1 and 3, okay. So we will have the updated form of augmented matrix where the third row has taken the first position, so it is 1, and then we got the second row is at the second position, and then we got the third row, which is like this. So uh, this is the first step of the partial pivoting, okay. So now we can just choose this as a pivot element, and we'll do the ray operation that we developed in the last lecture to make this as 0, okay. It's already 0, okay, so we don't have to do operation over here, okay. So but for example, if we just take the same problem, and rather than a 0 over here, if I just replace with a number which is 1, okay. So if you using a traditional Gauss elimination, okay, you'll say, okay, just make it both as 0, okay, and then we can proceed with an example to the next pivot element. But a Gauss elimination with the partial pivoting says, no, you can't proceed with this. You have to change the row which contains the bigger number in this particular column as compared to the number 1, okay, and which is again the minus 5. So what we're going to do is we're going to swap the rows 1 and 3, and we got over here as a 1 value because I just changed it, okay. So now you have to perform the Gauss elimination, okay, and then you have moved to the next pivot element after doing the making them as 0. Then you have to see at this pivot element is this number, because you have to look below the pivot element, okay. You can't look up the pivot element, you have to look down the pivot element, okay. So once you will be at this position, you will look up to this point, okay, is it greater than enough in magnitude than the number over here or not. If it is greater than, then you will swap these two, okay, and then you perform the making this particular element as 0, okay. So it's just a quick example. Please complete this example in this particular observation, okay, and find the solution of the equation, okay. Okay, this was from the the Gauss elimination. Now we're coming to the next topic, which is the LU factorization. Okay, so our problem is so we call it as a matrix equation. Okay, this is the matrix equation where A is the coefficient matrix, X is the unknown vector, and B is the right hand side. Okay, so this is our topic that we are actually doing, the linear system of equations. Okay, so what LU factorization says, let me just write over here. We have gone through obviously this topic before in the previous course. Okay, I'll just try to revisit it quickly, and then we wanted to deploy the partial pivoting over here. Okay, so what was the LU factorization for the given equation number 1? Okay, which is the our topic. we convert. So this is the step number one. uh, Convert A into the product of two matrices, which is a lower triangular matrix and upper triangular matrix. Okay, we have to convert matrix A into this particular product. Okay, uh, then once we have a converted form, so let me just write over here by taking an example that, for example, A is A11, A12, A13. So I'm just considering, for sake of discussion, a matrix of 3 cross 3 size. Okay, so A22, A23, and A21, A22, and A23. Then we have A31, A32, and A33. Okay, we got a matrix A. So once we completed the step number one, uh, the lower triangular matrix and an upper triangular matrix will be, let me just write, this is L11 0 0, L21 L22 0, L31 L32, and L33. So this will be in such a shape, the lower triangular matrix, and the upper triangular matrix will be U11, U12, and U13. U33. Okay. So once we have done this, we'll see such a form. Okay. What is a step number two? So we'll come to how to convert a matrix into LU form. So step number two is, um, let's say I plug this conversion into the main equation. So Ax is equals to B implies Lux is equals to B. Okay, because I've just replaced A with product L and U. Okay, now if you just see this equation number two, um, uh, let's see what is Ux. First, let's see this. What is, by the way, if you just see this particular example, what is the size of U? It is 3 cross 3. Okay, so size of A is 3 cross 3, and L and U both have the same size as of A. Okay, and it means we will have three unknowns. Okay, because we're solving three equations, so there will be three unknowns. So the unknown vector will be like this: x1, x2, and x3. So it will got three rows and one column. So it will be 3 cross 1. Okay. Now if I multiply u into x, the product will be of what size? 3 cross 1. Okay. So it means, let me say ux is going to be some y, and the size of y is same as size of x. And what is y? Let me just name it something which is, generally speaking, y1, y2, y3. It will be some 3 cross 1 matrix, so let it be any numbers y1, y2, and y3. So this is my equation number 3. Now if I use ux equals to y in equation number 2, it will be Ly equals to B. Okay, which is my equation number 4. Okay, my objective is to solve the equation number 1, and in trying to do that I have two more equations which are 3 and 4. Okay, now once you try to solve the equation number 4, okay, you will see that, okay, so let me write over here. Okay, so look at the equation number 4. 4 says Ly is equals to B. Okay. Now, whenever I try to solve a problem, I just written an example before when I tried to solve the Gauss elimination. So I'll know what is the value for B, okay, which is on the right hand side. Okay, I know I know what is A, which is the coefficient matrix, and I have converted A into a product of lower and upper. So I know the value of the lower triangular matrix. Okay, I know the value of B. So it will be like this: L11 0 0, L21 L22 0, L31 L32 and L3. So let me write y is y1, y2 and y3, and let's say b is b1, b2 and b3. So if you just see this, okay, and if I ask you, can you find the value of y, can we do that? So if I write the first equation from here, first equation, I'm just going back to the equation form, okay. So what is the first equation, by the way? First equation is L11 into Y1 is equals to B1. You'll be able to find the value of Y1 from here, okay. Then from the second equation, so I need a space, I'm going to, okay. So if you just go to the second equation, it says L21 Lxy1 plus L22 y2, and the next term is 0, is equals to B2. Now you know the value of now we you know the value of y1 from here, okay. You can plug it over there, and then you will get the value of y2, and then you will get the value of y3 from the last equation. The thing is, when you have a matrix which is a lower triangular matrix, then you will be able to find the y. Okay, once you will be able to find the y, you look into the equation number 3. So what 3 says? 3 says ux is equals to y. What is u? U is a matrix u11, u12, u13, 0, u22, u23, and then this particular matrix. What is x? X is actually the unknown vector we wanted to find, and this will be y1, y2, and y. Sorry, yeah, y1, y. So now you see, here you done the upward substitution. You started from the first equation, you find the y1, then y2, and then y3. Now what you're going to do? You're going to do as you did in the Gauss elimination. You do the backward substitution. You will first try to solve the last equation. You will get the value of x3. Then you will get the value of x2. Then you will get the value of x1. So in this particular process, by converting equation 1 into 3 and 4, we will be able to get the unknown vector x. Okay. The first question that possibly can come in your mind is, why we're using LU factorization than the Gauss elimination. Okay. So the answer is, computationally it takes less time, or actually working as compared to the Gauss elimination. Okay. So when you for example, the operation, the order of the Gauss elimination is n cube, and order of LU factorization is 2n square. What is n cube? It means if you have a 3 cross 3 system, we will have to do approximately 27 operations to get to the solution using the Gauss elimination. Okay, and we have to use 2 into 3 square operations, which are 18, to get to the solution through the LU factorization. For the larger systems, that's why LU factorization is better. When I say a larger system, n cube will be getting a very big value as compared to 2n square. Okay, so that's why computationally we prefer the LU factorization. Now, coming to a thing which is step number 1, how to convert it, how to convert a matrix into an LU form. Okay. Then we know the process. Once we have converted, then we have to use these two equations to get to the answer. Okay. So let me take an example, which is 10x1 minus x2 minus x3 is equals to 8, and then we have minus 2x1 plus 10x2 minus x3 is equals to 7. And okay, for example, this is the problem and we wanted to solve by LU factorization. Okay. Now, what is the step number one? Step number one is convert the coefficient matrix in an LU form. Okay. What is the coefficient matrix? It is 10, minus 1, minus 1, minus 2, 10, minus 1, minus 1, minus 3, and 9. Okay. So we start not with an augmented matrix, but with the coefficient matrix. Okay. We'll see later on, this is also somehow a significance of the LU factorization. Okay. Okay, this is the matrix A. Now I have to convert into the product, which is L and U. Okay. So let me write a general matrix of lower triangular matrix, which is I've just written before over here. It is L11, 0, 0. Then we have L21, L22, L3, 3. Okay, and then we have a U11, U12, U13, 0, U22, and U23, and then U33. So this is the step. That's how you're going to proceed. Whenever you try to solve a problem, you just write a coefficient matrix, and of the same order, you're going to write the lower and upper triangular matrices. Okay. So after doing this, now you see we have to find these LIIs, LIJs, and UIJs. Okay. How many they are? So we got 6 here and a 6 here. So total unknowns are 12 unknowns. There are 12 unknowns on the right hand side. Once we multiply a 3 cross 3 matrix with a 3 cross 3 matrix, it will be again a 3 cross 3 matrix. So we're going to compare, because both matrices are same, we are going to compare the entries. Okay. Please close the door. Okay. So we are going to have the 9 entries on this side, 9 entries on this side. Okay. So we're going to compare them. In other words, we got 12 unknowns and we got 9 equations. Okay. So we got 12 unknowns and we got 9 equations. If such a scenario occurs, we have to assume the values of certain unknowns as some real number or whatever. We will have a difficulty. For example, if I write x plus y is equals to 1 in the real number system, if I ask you how many unknowns we have, 2. Okay. How many equations we have, 1. How many solutions we can have? So you see, as many solutions as the possibilities of x. So if x is a real number, you'll see you got so many solutions. Okay. Actually, all the solution on the line y is equals to 1 minus x. The solution constitute a line. Okay. So that is a solution line actually. So whenever you got more unknowns than the equation, then there is a possibility of infinite many solutions. Okay. We don't want it, because we want a unique solution if it exists, if the determinant is non-zero, we want that. So the condition we're going to impose is either take LIIs as 1. This is a scenario 1. A second scenario is take UIIs as 1. Okay. So you see, if for example, I, rather than on the lower triangular matrix, please see over here. So at the main diagonal, what is LII? LII means L11, L22, and L33. So I'm going to write 1, 1, and 1. So if I write like this, it is now how many unknowns we have? 9, and we're going to have 9 equations. Okay. So either we can go with this process, or we can impose the condition that the UIIs are 1. We have to go with either of the one. Okay. We can't take both. Okay. Okay, so how to convert a matrix into an LU form? Just write the lower and upper triangular matrix, and then impose a condition that let's say on the main diagonals of lower triangular we're going to take the value 1. So L11 is 1, L22 is 1, and L33 is 1. Okay, so if for example I impose this condition, you see on the right hand side, or if I just now multiply both the matrices, what I'm going to get? U11, okay, if I multiply this row with this column, then I'm going to get L21, U11, then I'm going to get L31, U11. If I multiply this row with this column, you're going to get this entry, okay? So you see L21 multiplied by U11 plus 1 into 0 plus 0 into 0, okay? It's just a matrix multiplication. So if I go to the now this particular position, this position is what? This is the first row, and this is the first row and the second column. So multiply the first row with the second column, okay? So I'll get U1, 2. Okay, if I multiply the second row with the second column, I'm going to get this entry, which is L21 U12 plus U22, and then L31 U12 plus L32 U22, and similarly here U13 and L21 U13 plus U23, and this is L31 U13 plus L32 U23 plus U33. And on the right hand side, we have this matrix A, which is 10, minus 1, minus 1, minus 2, 10, and minus 1. It's if you just have a certain confusion, it's just the matrix multiplication. Okay, it's just the matrix multiplication. Okay, nothing else. So now you see a matrix on the right hand side, 3 cross 3. Matrix on the left hand side, you got a 3 cross 3. If they are equal, each entry will be equal. It means what is the value of U11? 10. What is the value of U12? Minus 1. What is the value of U13? It is minus 1. Okay. What is the value of L21? It will be L21 into U11 will be minus 2. We know the value of U11, which is 10, so we'll get the L21. Okay. So with this particular, so this is simple. You need to solve the equations, these equations, which is you know the value of U11, you know the value of U12, you know the value of U13, then you know the value of this particular product as minus 2. Okay, but you know the value of U11 as 10, so you get U21. Similarly, you'll get the value of L31. Okay, from here you'll get the value of L21. Okay, U22. Okay, so with solving these all equation, you'll be able to find all the unknowns. You have to plug those unknowns into this representation. Okay, so what is the step 1 of the LU factorization? Convert A into LU. So we just converted A into LU, then we'll follow the step number 2. So once we know what is L and U, then we can apply the equation number 4 to get Y, and then equation number 3 to get X with upward substitution and a backward substitution. We just seen in the for the generic case of 3 cross 3. Okay. So please complete this problem into as a homework. Okay, so please complete this particular example. We have done in this linear algebra course. Okay, it's not that difficult thing. Okay, so and also as a homework you have to do you have to compute rather than this scenario. Okay, so this is the first task that you have to do. The second task is I'm going to the same position when I start a problem. We have L11 here, L22 here, and L23 here. Now I'm going to impose a condition that rather than taking lower triangle main diagonal as 1, let's take upper diagonal matrix as 1. So if I just put this condition, now you have to solve a problem too with this. Okay, you also have to solve a problem. So this is as a homework, either use lower triangular main diagonal as 1 or the upper diagonal main diagonal as 1 values, and you have to solve a problem. No, at this point we have not done it. We'll see. So this is a traditional LU factorization. Okay, as we already learned the traditional Gauss elimination, and that we have improvised it. So we're going to improvise it. Okay, but it's just a revision of what is LU factorization. Okay. So with this, okay. By the way, there are certain names which is uh, Crout's factorization. So we know the procedure. I'm just going to name it, and it's Doolittle factorization. So if you just take the lower diagonal elements as 1, main diagonal, it's a Crout factorization, otherwise it's a Doolittle factorization. We know the procedure, these are just the names. Okay. If we just impose the condition that the lower diagonal as 1, okay, it's a Crout's, otherwise it's a Doolittle. Okay, factorization. So this is a traditional LU factorization. But you see, when you try to solve it, you have to divide by L11 or a U11. Okay, either using a Crout's or a Doolittle's factorization. Once you're trying to solve to get the numbers L21, L22, U22, okay, you have to going to divide by certain numbers. Okay, and those numbers are again the main diagonal elements. Okay, they are the main diagonal elements. So we come to the same thing. If with the numbers we're going to divide are smaller in magnitude, then they can pose a threat for a big error. Okay, that small error can contribute a lot when we apply so many operations till the end. Okay. So for example, when we are trying to find the value, for example, in the problem we just did, whenever I need to find the value of this coefficient, when I equate it to 10, you have to divide by certain number. Okay, you have to divide. Once you're solving those equation, you'll be taking some terms onto the right hand side, then you have to divide by certain number. Okay, then you have to divide by that certain number. That if you divide by that certain number, and if that number is obviously smaller in magnitude, how can we avoid it? Okay, because this is a same issue that we encounter with the Gauss elimination. Okay, as a pivoting problem. So the procedure we're going to do is called LU factorization with partial pivoting. Okay, we're going to do this. Okay. Okay, for this I'm going to take another example which might be of a 4x4 system. Okay. So let me take an example. I've just calculated it. We try to learn through an example. Okay, I'm just going to write the coefficient matrix, which is 2, 3, 1, 5. Then we have 6, 13, 5, and 19. And the third row is like this. And the final row is 4, 10, 11, 31. You see, when I did a previous example and I'm doing another example, I'm just considering the coefficient matrix. When you try to solve the Gauss elimination, you take an augmented matrix. Okay, so you see in in LU factorization, just try to understand in this way. For example, I'm only dealing with the coefficient matrix. If, for example, the right hand side is changing, okay, I can apply the same observation on that problem too. For example, we're solving the Gauss elimination. We're solving with the Gauss elimination. The previous example I just written. we have to take the right hand side too, augmented matrix. In the augmented matrix we have to carry it, okay. But in the LU factorization we only do the process with the coefficient matrix. We do not engage the right hand side, we engage it after we convert the matrix into an LU form. So in other words, LU factorization is applicable on a problem where the coefficient matrix is same but the right hand side is changing. So you can solve actually more problems by changing a same coefficient matrix into an LU form, okay. If the right hand side is changing, the coefficient matrix will remain the same because we have just converted it, okay. So but in Gauss elimination we can't do that because we have to carry the right hand side, okay. So that is again a benefit of the LU factorization. So I'm just going to do the process of LU factorization with partial pivoting. It's a mixture of a Gauss elimination and LU factorization, okay. It is also called, by the way, it is also called LU factorization with Gauss elimination, okay. So we're going to merge the both methods, okay. Okay, finally what I wanted is I wanted to convert it into an LU form, okay. So I want ultimately a lower triangle matrix and upper triangle matrix. So what I'm going to write now is step number 1, how to arrive to lower and upper triangle matrix, okay. So it starts with an observation, which is, let's call this U as A. At this point, A is not an upper triangular matrix, but we want to convert A into an upper triangular matrix. So I'm just naming it at U. Ultimately, we'll make it as the upper triangular matrix. And what is a lower triangular matrix? It will be an identity matrix of the size of the coefficient matrix, okay. So I'm considering lower triangular matrix and identity matrix, and then I'm also taking a special matrix over here. We'll see its significance once we arrive at this endpoint. It is called a permutation matrix, and it is again the identity matrix of the same size as of the coefficient matrix A, okay. So I'm going to write all these matrices, which is U, L, and P over here. So let me write U, which is 2, 3, 1, 5. I'll use a little less space so we can actually complete the process on this board. We have 4, 10, 11, and okay. Then we have a lower matrix as, it's an identity matrix. Hopefully you know what is an identity matrix. It's the easiest one to remember. Okay. And P is also the same, which is identity matrix of the same size as the size of A. Okay. A lot of numbers. Now, this is a step number 1. What is a step number 2? Step number 2 is uh, apply the row operations with partial pivoting on matrix U. So apply the row operations to make this U as an upper diagonal matrix. And you know, this is the step number 1 of the Gauss elimination. It converts a coefficient matrix A into an upper diagonal matrix. If you see the result of the step 1 of the Gauss elimination, it is what? Ultimately, we got an upper triangular matrix. Okay. Then the step 2 is the backward substitution. So, but here the observation is that apply the pivoting strategy. Okay. So here we see, okay, this is a qualifying pivot element, but we see a number which is bigger in magnitude than 2. So we're going to do what? Swap rows 1 and 2. Okay, swap the rows. So if I just swap the rows, so it will be 6, 13, 5, 19. And we got 2, 3, 1, 5, 2, 19, 10, 23, and then we have 4, 10, 11, and 31. Now we are not going to do anything to this particular matrix, which is a lower triangular, we call it as a lower triangular matrix. Okay, but we have changed the rows. We have changed the rows of the original matrix A. Now this is not the original matrix A, it has been changed. So the first row and the second row has been swapped. Okay, so I am going, so this special matrix P will take care of a thing that whenever we try to swap a row, it is going to swap at rows, the same rows. Okay, so I'm going to swap the rows of matrix P, and we'll know why we don't swap the rows of the lower triangular matrix. We'll see in the next process. So I'm going to change the rows of the matrix P. So we got this, then we have this. So you see, I just changed the rows first and second that I did with the matrix U. 0, 1. Now I have a pivot element. Using this pivot element, I'll do the row operations as I did in the Gauss elimination. And resultantly, what I got U as, so there is no changes to there are no changes on to the row number 1. So there are no changes in row number 1. So there are no changes in row number 1 of a lower triangular matrix. We have to do the same operation on these two matrices. Okay. This matrix is only taking care of swapping of rows. We don't have to do anything to this matrix P. Okay, it's just taking care how the original matrix A is being changed. Okay, so we're going to do the row operation on this matrix and this matrix. If I do the row operations, I got 0, 2 by 3, 2 by 3, and 16 by 3, and then so I'm just going to write the calculated values. $18.33. Obviously, the same operation that we did here are going to occur over here, okay, onto the lower triangle matrix. And we got the shape like this, which is 1 by 3, 1, 0, 0. Then we got 2 by 3, again, sorry, 1 by 3, 0, 1, 0. And then there is 2 by 3, 0, 0, 1. If you don't see a changes in these indices, okay, in these indices, that is due to the reasons because we got the zeros over here. So whenever we try to get the subtraction multiplying by the number, that number is 0, so we're getting the same things onto this scenario. But that matrix will remain the same because we don't have to do in the row operations. We just have, whenever we try to swap the rows, we're going to reflect that observation onto the permutation matrix. So it is 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay. Now the pivot element will move to this position because we have done with the first pivot element, and it says let's look up to the numbers which is below in this column. Is there is a bigger number in magnitude? Yes, there is 16.67. So what we're going to do? We're going to swap row number. So we're going to swap row number 2 and 3. So the observation is swap rows 2 and 3. And by the way, it's row 2 minus, okay, yeah. Over here, I think. You're right, I think, hopefully. Because it will be row 2 minus row 1, okay. So, okay, right. Okay, so we got this over here. Now I am going to swap the rows, which is second and third row. Okay, so these two matrices are somehow linked in a way that whenever I do the row operations, then I reflect on this particular matrix, and if I do the swapping of the rows, I reflect on this matrix. Okay, so let me going to write over here a matrix U, which is 6, 13, 5, and 19, 0, 2 by 3, 2 by 3, and 16 by 3. Sorry, we have to swap the rows. Okay, so let me write the swap row, which is 0, 16.67. Please, if anyone can just call the numbers 8.6, 16.67. So 0, uh, 2 by 3, 2 by 3, 16 by 3, and the last row is 1.33. Okay, 0, 7.67, 18.3. Thank you so much. Okay, so we have the matrix L. We don't have to do anything to this matrix because there is a swapping of rows, and we have to reflect it somewhere else. Okay, so we just swap the two rows, which are second and third row, and we don't have to reflect it over here. We have to reflect in this P matrix. Okay, swapping of rows, we have to reflect it. I've just reflected it over here. Now you will see this is the pivot element, and we'll use this to make these two elements as 0. Okay, and then we'll move to the next pivot element. Okay, we're going to see is we got a number bigger than that. If it is there, then we'll swap the rows 3 and 4. Otherwise, we'll just intact it here and make it as 0. Okay, and then we stop. So finally, I'm just going to write finally. You have to please check it. I'm going to the matrix U, going to get the matrix U, which is 6, 13, 5, and 19. Please do homework, just complete this particular and make sure that we got the same numbers I'm just writing. Okay, so you have to do there are two steps over here. Okay, you have to do that. So 0 and 3.83, and the lower matrix is 1 0 0 0. Then we have minus 1 by 3, 1 0 0, minus 1 by 3, 0 0.04, 1 0, and minus 2 by 3, 0.08. There can be a mistake. Please, when you confirm it from your working, be able to see. Okay, what is P? P is 0 1 0 0 and 0 0 1 0. You got 1 0 0 0 and sorry, it's yeah 1 0 0 0 and then we got 0 0 0 1. Finally, this will be the form. Okay. Now you see, when we name the A as U, we made that as an upper triangular matrix. We make it as an upper triangular matrix. Okay, and this is a lower triangular matrix. Okay, you got a lower triangular matrix, and you got a permutation matrix. You see, if I do the row operation, swapping of rows over here, then this number 1 can go over there, because if I just swap these two rows, that one can go over there, then it will not be a lower triangular matrix. Okay, that's why we do not swap the rows of the matrix L. Okay, we make track it by introducing a new matrix, which is permutation matrix. Okay, now you see we have converted a matrix, and it has done with the partial pivoting. And if our original equation is what, by the way, we have A, okay, x equals to B, and I have converted into A into LU form. But if you multiply this lower triangular matrix and upper triangular matrix, you will not get A, but you will get PA. Okay, because now just understand in this way, this P just said it that okay, originally whatever the A is, now the row number 1 comes at row number 3. The original A, in the original A, the row 1 has come to the row number 3. Just understand in this way. The row 2 is come at the first position, the row 3 come to the second position, and the last row is it at the last position. So this actually matrix with the position of a 1 just tell you, okay, that how A has been translated. Okay, there is a translation in it. Okay, because that translation is just that rows are being swapped. Okay, so this is actually PA is equals to LU. Okay, so this PA will just adjust the rows of A in a same manner that we did the operation. So this is the partial pivoting LU factorization. So we're done with the help of a certain portion of the Gauss elimination. Okay, so with this we can avoid actually the error propagation that come with the round of error. Okay, now just a quickly a 1 minute, just a 1 minute. So if you just go to the MATLAB, okay, and write linear solve command, it will just solve you the matrix. Okay, for that I'll just take some moment, okay, to write a matrix A, which is if you see this example, which is the mass balance problem. Okay, that is the problem we take in the example number in the lecture number 1. Okay, so if you just go to the mass balance problem, this is the equation that you see over there, and the numbers has been given in the problem. So the system that becomes that you need to solve is this matrix. Okay, so if I just write this matrix into the MATLAB, so it is 0.04, and then we got 0.54 and 0.26. In the next row I got 0.93, 0.24 and 0, and then in the final row I got 0.03, 0.24, 0.22 and 0.74. So this is the matrix A. Okay, and then the right hand side is what? It is 262. Okay, so I just write 2, 6 and 2 because it's a column vector, so I just take a transpose. Okay, So this is B. Now if you just use linear solve command in MATLAB and just write A and B, it will give you a solution. Okay, the value of the x1, the value of an x2, and a value of x3. Okay, and if you just write, if you just use a command which is so this command is LU, and you give a coefficient matrix A. It will convert A into LU form. Okay, so you see it will give you a lower triangle, upper triangle, and upper permutation matrix. Okay, so this is the same problem that is of the mass balance. Okay, and you can just solve by using the two commands. Either just directly use the linear solve command, and by the way, the linear solve command make use of pivoting, partial pivoting strategy. So in build, the partial pivoting strategy is over there. It uses a Gauss elimination or the LU factorization with the partial pivoting. Okay, it's solved with a partial pivoting. So there are some well conditioned matrices you can see onto to the worksheet that actually I've shared with you on to LMS. You can see that there is a one document that's shared over there. You can read about the well condition. But just to conclude this lecture, in this particular lecture we able to identify the significance of the rounding actually and the partial pivoting. We have learned about the traditional LU factorization, that is the Crout factorization or Doolittle factorization, and then we can modify it to with this the pivoting strategy. Okay, so thank you so much.